Welcome, dear students, in the fifth video of refraction of light. In this video, I am going to explain about critical angle and total internal reflection. So let us start critical angle. As we know, when a ray of light travels from denser medium to rarer medium, it bends away from the normal. Let us see. Like suppose AB is a interface or a surface which separates two medium. Let upside is rarer and this side is a denser medium. Suppose one normal is there. I am taking a normal at this point. As we know, when a ray of light travels from denser medium to rarer medium, it bends away from the normal. It is bending away. This angle is angle of incidence and this is the angle of refraction. As we will increase the angle of incidence like that. Angle of incidence is more. So angle of refraction will also increases. Similarly, if for a particular angle of incidence, that means I, if the angle of refraction becomes 90 degree, then this I or angle of incidence is called the critical angle. Let us see how. Suppose AB is an interface or a surface separates two medium. Let this side is rarer, say air, and this side is denser, let glass. One normal I am taking. Suppose a normal at point O. If a ray of light is traveling from denser medium to rarer medium, this is angle of incidence I. For a particular angle of incidence, if I equals to C, then the angle of refraction becomes 90 degree. This R equals to 90 degree. Then this angle is called the critical angle. So we can define critical angle as critical angle is the angle of incidence in the denser medium for which the angle of refraction becomes 90 degree. So this is the critical angle. Now let us derive a relationship between critical angle and the refractive index of the medium. So let us see the relation. We will write the relationship. Relationship or relation between critical angle C and refractive index mu of the medium. So let us derive the relation. According to Snell's law, we know that mu Ag, refractive index of second medium with respect to first medium, equals to sin I by sin R. If I equals to C, angle of incidence equals to critical angle, then we know that angle of refraction equals to 90 degree. So let us substitute these two values in this equation. So we will get mu Az equals to sin C by sin R. Sorry, sin C by sin 90. As we know sin 90 equals to 1, so we can write mu Az equals to sin C. According to principle of reversibility, we know that mu Az equals to 1 by mu Ga. So we will substitute this value in this. So we will get mu 1 by mu Ga equals to sin C. So this is the relationship between refractive index of the medium and the critical angle. Now let us see the factors affecting the critical angle, or the factors on which the critical angle depends. As we have seen from this relation, sin C, that means critical angle, depends on the refractive index of the medium, and we know refractive index of a medium depends on the two factors, that is temperature and the wavelength or the color of light. So two factors on which the critical angle depends, that is, first one is temperature. As we know, as the temperature increases, refractive index of the medium decreases. Therefore, the critical angle increases. So we can say directly, critical angle increases with increase in temperature of the medium. Second factor, wavelength or the color of light. For as the wavelength increases, refractive index decreases. So again we can say critical angle increases with increase in the wavelength of light. Now let us see total internal reflection, TIR. As we have seen, critical angle, the angle of refraction, for critical angle of refraction becomes 90 degree. Let AB is an interface separating two medium. Consider rarer medium and this is denser medium. Say air and glass. Let us draw a normal at point O. If the angle of incidence becomes greater than critical angle, let us see how. Suppose a ray of light is incident at this point and I is greater than C. Angle of incidence is greater than critical angle. As we know, if I equals to C, angle of refraction becomes 90 degree. When I is greater than C, then we will find that no any ray get refracted in the rarer medium. All the ray of light reflected back in the same medium. This phenomenon is called the total internal reflection. So we can define total internal reflection as when a ray of light travels from denser medium to rarer medium, the angle of incidence becomes greater than the critical angle for the given pair of media, then no any ray get refracted, all the rays get reflected back in the same medium. This phenomenon is called the total internal reflection. Now we will see the conditions for total internal reflection. There are two conditions for total internal reflection. The first one is ray must travel from denser medium to rarer medium. Ray must travel from denser medium to rarer medium. First condition. Second condition is the angle of incidence must be greater than the critical angle. So these are the two conditions for TIR, total internal reflection. Now let us see total internal reflection through a glass prism. In this, first we will see total internal reflection through an isosceles right angled glass prism. So let us see the total internal reflection through right angled isosceles prism. Right angled isosceles prism is also called total reflecting prism or totally reflecting prism. This in this as it is isosceles, so one angle is 90 degree and two is 45 degree. Let us see how the rays are got reflected. Let a ray of light is incident normal 90 degree to this. So as it is entering 90 degree, so what happens? The 90 degree normal, as we know, there will be no any deviation in the path. Let us draw one normal at this point. Let one normal at this point. We know this angle is 45, this is 90, so this will again become 45 degree and normal 90 degree, so this angle also 45 degree. For a glass, the critical angle is 41.8 degree. As it is 45 degree, so approximately we can take critical angle for glass 42 degree. So as it is more than 42 degree, means more than critical angle, so the ray will not refract, it will reflect back. So the ray of light will reflect back in this medium by an angle of 45 degree. So again this angle will become 45. And as it is 45, so there will be 90 degree and it will come out by this way. So this is total internal reflections takes place at point A. If we will show for a body, or as we can say from this figure, this prism deviates the ray of light by an angle of 90 degree. So if object will be placed here, that means if AB is the object, it will be seen in this direction, that is AB. So object, that means isosceles prism, in this case it deviates the ray of light by an angle of 90 degree. Let us see the next. If a ray of light is incident in this way, like that, suppose there is again 90 degree. If at 90 degree it incident, without refraction it will go. At this point, let us draw one normal. As we know, this angle 45, it is 90, so this will be again 45 and this angle is also 45. So again angle of incidence is greater than critical angle, so the ray will again get reflected back. So it is reflected back. Look at this, again from this surface the medium is changing. We can find this is 45, this is also 45 and this is also 45. So this angle will become 90 and normal, then it will go straight without any deviation. If we will show the another ray for this, it will also pass like that, like that. Suppose there is an object AB, we can see it in this way, that is A dash and B dash. So in this case we can find the object is get inverted. This phenomenon or this application is used for erecting the object. If an object is inverted, we can see its erect image by this application. Let us see one more. If a ray of light is incident in this way, up from 90 degree there, so 90 degree it will get entered without any deviation. Let us draw one normal at this point. 45, 90, 45, so this will again 45, which is greater than the critical angle. So the ray of light get reflected back by an angle of 45 degree in this way. So this angle is also 45. At this point again the medium is changing, so we will draw one more normal at this point, one more normal, as it is, as we will find this point also at 45 degree, and as this is 45, this is 90, so this will be 45, so this will be also 45. Now again it is greater than critical angle, so ray will again deviate back, now 90 degree, so it will come back in this way. This is also showing the total internal reflection. For another ray, if I will show, it is moving up, then in this way, and then down. So in this case we are finding the object is, the ray of light is get deviated by 180 degree. Look at this. In this case the ray of light deviates by 90 degree. In this case the ray of light deviates by 180 degree, and this is used for erecting the object. So right angled isosceles prism can be used for three purposes. The first one, to deviate a ray of light by 90 degree, to deviate the ray of light through 180 degree, and to erect the object. Now let us talk about different applications of total internal reflection. We have seen in this prism. Let us talk the other applications. Sparkling of diamond. Diamond sparkles due to the total internal reflection. We have formation of mirage. What is mirage? It is an optical illusion of water observed generally in desert when the inverted image of an object is observed along with the object itself on a hot day. So we will find that means one illusion of water along with that object also. So this is mirage. Next other things, if we are finding if there is a crack in the glass, so it often shines like a mirror. So this is also one application of total internal reflection. An optical fiber is used to transmit a light signal over a long distance without any loss of energy. So these are different applications of TIR. In this I already explained about critical angle, total internal reflection, refraction through right angled isosceles prism, and some applications of TIR. Thank you students. Thank you for watching.